It has been a while. Say hello to Theodore. He is sleeping for some reason, sleeping during lectures, unlike all of you who I'm sure are wide awake for these fascinating lectures on counting. Not a sentence that you'd probably expect to hear in a college class, but here we are. So let's get into partial permutations, which are a little bit more interesting. So let's say that you have 10 things on your to-do list. Okay, you got 10 things that you need to do, but you only have time for 5 of them. We've all been there. And you're curious about how many ways can you order those 5 things. Again, each thing could have 10 options, but you only have time for 5 of them. So we're really only caring about those top 5 things, your top 5 priorities for today. Well, it's the fundamental theorem of counting again, not calculus. All right, let's break this up. You have time for 5 things today. Well, how many choices do you have for the first thing you do that day? Well, you have 10 choices. How about the second thing? You have 9 choices. The third thing, 8 choices. The fourth thing, 7 choices. The fifth thing, 6 choices. And you might be tempted to go on and on and on. But you don't have all day. You only have time for 5 things. These are 5 things. This is how many ways you can order those 10 things into 5. All right, this is a partial permutation. Okay, I actually don't know what number this is, but I have Desmos ready. This is 10. Well, let's say I don't want to type this many things. What's a different way of writing this? Well, there are many, many, many different ways of writing this. And that's what we're going into here. So one of them, let's say, well, all right, I just won't be lazy. I wanted to kind of make this exciting and tie this into the next thing, but I don't want to keep y'all on this cliffhanger for so long. You're curious about how many ways there is to order your to-do list. The answer is over 30,000. 30,240. Whew. There's a lot of different ways of getting things done today, which if you're like me, that sounds overwhelming. Just pick something. Just get something going. No analysis paralysis for us today, right? Okay, so what does this look like? All right, so let's say you have n things and you can only fit 5 of them. All right, so n things possible. Let's say there's only room for k of them. How do we write that? Well, let's generalize this. Okay, so the notation that we're going to be using is permutations, partial permutations of n and k. So these are subscripts. So this is a little p and then a subscript of n, comma, subscript k. And that's one way of writing it. There's a lot of different ways of writing permutations. And what this is, well, what happened? It's like a factorial, right? You know, it's n times n minus 1 times n minus 2. It's like a factorial. It just doesn't go down as far. What's the last term that we get here? Well, here, this was, n was 10. This was 6. But k was 5. So it's not just 10 minus 5. It's 1 more than 10 minus 5, right? That's the last one. 1 more than 10 minus 5. So it all goes down to 1 more than n minus k. That's what a permutation is. You may have also seen this notation before if you've seen it. It's n factorial divided by n minus k factorial. And this formula looks more complicated than it really is. Basically, n factorial has all of the integers below n. And this has all the integers like n minus k or below. So really, we're just getting cancellation starting with n minus k. And that's why it works out. So there's not actually a fraction. This is just a way of writing that cancellation. Like 10 factorial would have all the numbers 10 down to 1. But we're dividing by 5 factorial because that's why the 5 cancels and the 4 cancels. That's why there's no 5 or 4 here. So that's another way of writing it. Another way of writing it, and this is cool notation that I actually haven't seen before. Oops, let's use n, is n to the k falling. So it's like an exponent, but it's an underlined exponent, and it means n to the k falling. And it's really quite cool. I think it's fun. I have not seen this before. But let's look at that, right? If I have something like 10 to the 5th falling like we just did, what does that mean? That means there's 5 things multiplied by each other, but the thing is falling each time. So compare that with regular 10 to the 5th. That would be 10 times 10 times 10 times 10 times 10. Regular exponents are just multiplying the same thing that many times. The falling exponent is still multiplying 5 times. Did I say doing it 10 times? I meant doing it 5 times. It's still doing it 5 times, but now the thing that we're multiplying by is falling every time. Okay? So, similarly, let's say we had 6 to the 4th falling. That would just be 6 times 5 times 4 times 3. It's like 6 to the 4th. There's still 4 of them, but now the thing is getting smaller every time. Again, 6 to the 4th regularly would just be 6 times 6 times 6 times 6. So it's a pretty cool notation, I think. But you can also just use any of these other notations as well. If you want to use like this notation as well, you can. If you want to use this is very traditional mathematical notation for permutations. But that's what we got here. So we're going to end with some questions. All right, and I want you to do these questions. I think you're more than capable of answering these questions. So I want you to pause the video and get these answers. We'll talk about them together, and then I'll wrap up the video. So how many ways are there of ordering the following? If you have 30 movies and you want to schedule a movie night with 3 of them, how many orders of movies for that movie night are there? Well, again, there's 30 options for the first movie, 29 options for the second movie, 28 options for the third movie. Maybe you write your answer like this, and then again, you type it into a calculator to get what it is. 30 times 29 times 28 is 24,360. There are a lot of possible schedules for your movie night. All right. Again, you could have written this differently. You could have said this is 30 cubed falling. This is also permutations of 30, 3. Okay. You could also calculate this as 30 factorial divided by n minus k. 30 minus 3 is 27 factorial. All of these are the same. This is your final answer, the number. There's many ways of getting to that number, but this is the final answer. If you just want to do it this way, that's perfectly fine. It's going to be a little harder when we have bigger numbers, like the next one. Let's say there's a race of 50 people, and we don't care about the bottom 40. We only care about the top 10. How many top 10 finishing places are possible? Well, again, there's 50 people that could be first, 49 people that could be second, all the way down to not 50, all the way down to 41. There's 41 people who could get 10th. And again, this is where things get a little hard to count. And it's probably just easier to use one of our notations, right? We're looking at how many permutations there are 50 people going into 10 spots. We could do that 50 factorial divided by 40 factorial. We could say this is 50 to the 10th falling. However we want to write it is okay. I think if you're typing something into a calculator, this is the easiest. Remember what this is. This is n factorial over n minus k factorial. N is how many things there are. K is how many places that we really care about. So right here, this was n. This was k. So 50 factorial over 40 factorial. This is going to be a big number, folks. 50 factorial divided by 40 factorial. Yep, that's big. 3.728 times 10 to the 16th. 3.728 times 10 to the 16th. That is a lot of zeros. So let's say you're working. You're working for a news place or whatever, and they're like, hey, Jason, I'm curious about I'm curious about all the ways that we could have a top 10 finish tomorrow. Can you make me a list of all the different ways for top 10 finishes? You look them straight in the eye and say, no way, Jose. I'm not making a list of 3.728 times 10 to the 16 things. That many lists, and each list has 10 things on it. That's too many lists. I don't care how much you love lists. This is too many lists. So you say, nope, not going to do that, boss. Sorry. Find someone else. Anyway, this is all if the order matters. If we don't care about the schedule and we just care about, well, how many ways are there of watching 3 movies? Like, how many groups of 3 movies are there? If we're just curious about who's moving on to the next race, not what order they place, just who's moving on to the next stage in the tournament, then the order doesn't matter. It just matters how many ways are there of grabbing without an order. And that's going to be the next topic. That's going to be the next video. That's called combinations. Here we're doing permutations where order matters. Next is combinations where the order doesn't matter. Let me know if you have any questions about this. Otherwise, I'll see you then. Have a good one.